Assalamualaikum. Today group 4 will present about kinetic of rigid body. Here is our group member, include Shaza, Farisha, Putri, Adib and Helmi.
My name is Muhammad Azul Halmi bin Abdullah. My metric ID is CD240069. So for the introduction, in this case study about the dynamic, we choose the real life world application that related with the kinetics of rigid body. Kinetic of the rigid body means movement of a rigid body under the influence of external force and moment. It involves analyzing the relationship between the force acting on the body, the resultant motion, and the body physical properties like mass, moment of inertia, and geometry. This case study aims to analyze the movement and mechanical stability of a float ball used as a water level control valve. What you can see in the picture, there is the system of the water pump lever. The study focused on the main component, namely the float ball and cylinder rod that support it. The float ball in this system is assumed to be spherical, made of stainless steel and connected to a cylinder rod of uniform material and dimensions. The system pivot about the fixed point, which is called point O, creating a rotational motion when the float ball is exposed to external force such as gravity, buoyancy, and fluid motion. The importance of the case study is to understanding the dynamic is crucial for ensuring system efficiency and longevity. For instance, excessive angular acceleration or high reaction force at the pivot point O can lead to mechanical failure over time. Additionally, the insight from this analysis can guide the design and optimization of water pump level system, ensuring they meet operational requirements while maintaining structural integrity. For the theoretical framework, this case study employs fundamental principles of rigid body dynamics, such as Newton's second law for rotational motion, the equations of motion, and force equilibrium to analyze the system behavior by systematically evaluating the system response to external force. The study aims to provide the comprehensive understanding of the mechanical performance of the float ball and cylinder rod mechanism. And then for the objective of this case study is to analyze the dynamic behavior of water pump level control system, which consists of a float ball and a cylinder rod pivoting about the fixed point. For the first objective is to calculate the maximum moment of inertia for the float ball and cylinder rod about the pivot point O. This step is crucial for understanding the system resistant to angular motion and its response to external force. And for the second objective, to determine the angular acceleration of the system's center of mass when subjected to external force. This analysis helps in understanding the motion of the dynamic of the system. For the third objective is to compute the reaction force at the pivot point O due to the combined effect of the float ball and cylinder rod. These forces are critical for assessing the structural stability and ensuring the durability of the system under operational conditions. And the last one is to derive insight into how the system parameters such as the size, material, and dimension of the float ball and cylinder rod affect its performance. This understanding can help in optimizing the design for improved efficiency and reliability in water level control application. Through this analysis, the study aims to apply principle of rigid body dynamic to a practical engineering system, bridging theoretical concept with the real-world application. The result will provide valuable information for designing and improving water pump level system to ensure their effectiveness and long-term functionality.
Next, we move to the part of methodology. The methodology section of the document provides a detailed analysis of a float ball valve system to understand the dynamics of rigid bodies, specifically a float ball and a cylinder rod. Key points include first about the system description. The float ball is modeled as a rigid sphere and the cylinder rod as a rigid body. Their connection is a pivot allowing free rotation. Second is about problem definition. The study focused on analyzing the forces and moments on the float ball and the reaction forces at the pivot point on the rod. Third is about mathematical modeling. First, we need to find the mass moment of inertia for the both, which is the sphere and the rod. We stay in the part of mathematical modeling. So, for the second, we can find the tangential acceleration is described as dependent on angular acceleration and the radial distance. Then we can find torque, which is related to the angular acceleration through the combined moment of inertia. For we can find the force components are divided into two, which is tangential and normal force. And the last is resultant force at the pivot point is derived for the vector sum of horizontal and vertical components.
As for the calculation, by applying the topic of kinetic rigid body, so we wanted to determine the mass of inertia, the angular acceleration, and also the force reaction at pin O. So according to this question, we change the value to the real life component value to get the answer. Firstly, to determine the mass moment of inertia, we have to draw a FBD, which is free body diagram. So as you guys can see here, I apply all the reaction as OY and OX, and then we have a angular acceleration movement and also the weight. So the weight is according to the real life component size. So firstly, we have to find the mass moment of inertia for float ball. So as given a weight, we have to find the mass. So here we have to find the mass by using weight over g, since weight is equal to mg. Then we get the answer of 0.517 kilogram. Then for the ball, we know that the mass moment of inertia is equal to 2 over 5 mr square. Then we just substitute all the values since the radius has been given and also the mass have been calculated, and get the answer for 8.7373 times 2 power negative 4 kg meter square. Then we find for the mass moment inertia slender rod, where we need to find the mass also by using weight is equal to mg and determine the m is equal to 0.306 kilogram. Then for the moments of inertia slender rod, we know it's 1 over 12 ml square, and we just substitute the value of mass and also the length as given is 150, but convert into a meter. Then we get the answer for 5.7375 times 2 power negative 4 kg meter square. Secondly, to determine the angular acceleration, according to the FBD, we have n and t direction. So firstly, for n direction, which is x-axis, where for the acceleration by the mass of center for ball and also rod, we determine that there is no angular velocity, which makes all the acceleration at n direction is 0. As for the tangential direction, which is y-axis of acceleration by the mass of center for ball and rod, has a value. So first of ball is acceleration is equal to alpha rb is equal to x alpha. Then we have rod, where acceleration is equal to alpha r rod is equal to y alpha. So what is the value x and y is where the point of center mass to the point O. So as I calculated here, x is equal to 215 millimeter and y is equal to 75 millimeter. Then to calculate the angular acceleration, we have to apply the total moment at O is equal to I alpha plus MAD. Since moment is equal to force times distance, so the weight of each ball and also slender rod has to multiply the distance of x and y. So as shown here, the 5.07 times 215 millimeter plus 3 and 75 times 10 to the power negative 3. So why is it positive? Because it is a anti-clockwise movement. Then it's equal to both of mass of moment inertia times alpha, which has been calculated just now, plus with the mass acceleration d. So the acceleration is based on the tangential direction just now, and we just multiply, and then we get the answer for angular acceleration is 48.6 radian per second square. Lastly, for the force reaction at pin O, by applying total F is equal to MA for each n and t direction. So firstly, for n direction, we know that there is no angular acceleration acted to the point O, so the OX is equal to 0 Newton. Then for t direction of y-axis, we apply total Fy is equal to MAY, and we have two weights that goes downwards. So we have negative 5.07 minus 3, where it's equal to mass times the acceleration of alpha RB. Then we just substitute the value of alpha that we have calculated, which is 48.6 times 250 millimeter, with the mass downward and also with the mass of the road. Then we get the answer of OY is equal to 1.55 Newton. And then finally, we determine the FO, which is the square root of OX square plus OY square. And we have determined FO is equal to OY, which is 1.55 Newton. Then for the analysis, we conclude the graph of comparison float ball and slender rod. So based on this graph, we choose three parameters, which is mass, size, and also mass moment of inertia. So the mass and size is given from the real life component size, which is the mass of float ball is were calculated that it is bigger than the slender rod, as shown here, 0.517 for float ball and 0.306 for slender rod. Then from the mass, if the mass is bigger, then the mass moment of inertia also for float ball also is bigger than the slender rod as calculated. But then the size of float ball is smaller than the slender rod.
This case study investigates the dynamics of a water tank's float valve, measuring mass moment of inertia, angular acceleration and force reaction using rigid bodies principles. The mass moment of inertia for the float ball and slender rod was calculated using real-world values. The results showed that the float ball had a higher mass moment of inertia due to its larger radius, as shown in the graph comparison in the 3.1 analysis. This measurement measures the resistance of the float ball and slender rod to rotational changes due to torque or external force. The mass moment of inertia for the float ball and slender rod was calculated, revealing that they are in motion due to applied torque or external force. The tangential direction of the float ball and the slender rod was also taken into account, resulting in an angular acceleration of 48.60 radian per second square counterclockwise, indicating the rotational response when torque of external force is applied. The reaction force at pin O, Fo, equals to 1.55 Newton, balances forces and moments produced by the float ball and slender rod, ensuring the efficiency of the water tank's float valve. This balance prevents the system from becoming unbalanced, verifying the precision of the theoretical model used to study its motion. The overall case study supports rigid body dynamics theory, aiding engineers in designing and optimizing float valve systems. For the future research, should consider frictional effects, experimental evaluation, and investigate different shapes of materials for improved system design and accuracy.
This study analyzed the mechanical behavior of a water tank float valve using mass moment of inertia, angular acceleration, and force reaction at pin O, based on actual observation. So the mass moment of inertia is used to measure a float valve resistant to rotational motion, assessing its stability and response to external force. It also measures the valve force under rotational motion, revealing it responds to dynamic input. Force reaction at pin O evaluate internal force at the hinge point, assessing stress concentration and ensuring component reliability under operating loads. This case study demonstrates the application of theoretical concept in engineering issue, particularly in the case of float valve. It underscores the importance of combining analytical technique with practical application for increased structural durability, performance, and design efficiency.